right, so let's get started. Hi, so today I'm going to talk about how to build multi-party computation or MPC securely on blockchains. So if you are interested in privacy-preserving machine learning, that's a topic that came up sometime earlier, or performing secure aggregation of the data. In all those environments, multi-party computation is a mechanism that allows you to do that. Basically, if you heard about fully homomorphic encryption or FHE, there's also one more topic which is basically just a sub-branch of multi-party computation. And my presentation today will talk about how to get some interesting guarantees in this environment and what to keep, what to be aware of when you're building such solution in blockchain space in general, and especially in the DePIN environment when you are collecting data, what kind of challenges that you can be considered in this space. So when we consider this threshold cryptography or multi-party computation problem that we require for any kind of a learning, the moment we want guarantee that we need data, we need the processing to finish, we want guarantee that we get output, and we don't, not a single party just destroy my computation and just make me do that again. These we call as robustness property. You require honest majority. Like you want 15% guys to be at least honest and be always present over there. But typically what happened, most of the solution in this space, as they started to build, at least from the academic background, consider what is known as a broadcast channel model, which means that you have magical access to some kind of broadcast channel, some kind of a bulletin board where you put things there and they are available to be used. Assuming that network keys or our internet is synchronous, that means it works at exact clock take. It says that I send a message, somebody else is going to receive that in exact same time, defined by my system. If you make such an assumption for the internet, indeed you can build such broadcast channels. However, that's not true for blockchains, as we are going to see, and that's not true for internet in general. And the question is that can we really consider internet or in general any network where we're building our solution in DePIN environment to be synchronous to build such protocols, such broadcast channels? And the answer is simply no, if you want high performance and low latency. So the idea is that, try to click, hopefully it will come soon, okay. Yeah. So unless we are fine with the latency of minutes, and probably you'll say, hang on, Sachin, I don't want to go for, we cannot assume internet to be synchronous. Okay, so what instead we want, consider that typical models that are more meaningful to call the internet is what we call as asynchrony, which means that there is no guarantee that message will read, but it will not get dropped. Eventually it will reach, like email. Sometimes you get email which is supposed to come yesterday, just came today. I know that it happened very irregularly, but it can happen. And the aim here is that to be prepared for that. So that's a synchronous model, asynchronous model, sorry. Or you assume a slightly weaker version of that called partial synchrony, where you say that it can be, for unknown amount of time, it can be slow, but afterwards it picks up and then things continue to work. And this unknown time is called GST, just a technical term, but the idea is that these are more meaningful models where we can build indeed internet-based protocols. And in such an environment, in general, the broadcast channels are not something which can be built in general. So I just here wrote down the definition. I won't go to the technical detail here, but my slides I can share with you if you want to understand in this here. And these are the definition we want for broadcast channel. And we can't achieve that in the model if we assume that to be not synchronous in general. And if you want to do MPC or all these tasks, then beyond synchrony on the real internet, then the typical one thing that's going to happen is that you can't solve this problem for only 51% honest party. You require much bigger super majority of them, like 67% of them to be honest for these things to work out. But not only that, it do make also the development a very cumbersome task, because you have to deal with what are known as common coins, have some kind of a randomization present, or timeouts and other things. Basically, it becomes, think in this way, if you want to, it's more like you want to build an SMR but private, or sorry, if you want to build a blockchain in private, so the task to become like easily 10 times more expensive in general. And easily, I'll say, if you start building it even with good expertise, it can be easily year or 2 years before which you can see something meaningful coming out from such an adventure. My aim from this discussion today is to show that there are interesting or easy way to build this solution on blockchains. We have to deal with some security mechanism, but it can be built. And my hope is to demonstrate that with some small examples, and for other things, I'll more say that this can be done, believe me. Okay. So there are already some solution which where they say we are going to build protocols on blockchains. It is already considered where we want to build this secure protocol on blockchain, but many of them still consider and call blockchains as broadcast channel. But in fact, they are not. So on the left-hand top, I have written a more formal definition. But what can blockchain offers you? And I want to really talk about those 3 informal points I've mentioned there. The first thing is that when I send a transaction, it will eventually appear. Okay, I can't give you any guarantee it will appear in a minute or 2. It may appear in milliseconds, but I can tell you that it will eventually appear once it reach enough RPC nodes or validators. But I can't give you guarantee when, okay? Because there are multiple events and incidents happening on blockchain. It's a shared environment, and I can't give you any guarantee when it's going to appear there, okay? Different people may see them at different point of time because everybody just sitting in different part of the world, okay? However, they all see them in same order. So if I saw your transaction in block 10, then others also going to see that in block 10. They may see block 10 after 20 minutes, after 10 minutes, but they are going to see it in the exact same order. So I know that I saw in block 10, so you are going to see in block 6. That's a nice guarantee that blockchains offer. And by the way, I'm using this term here, SMR or state machine replication. That's just a technical name for blockchain because like a blockchain like a state, and we're replicating that on different environment. That's the reason that term. So maybe in the talk I use SMR, you just think that in your term that it's a blockchain in general. All right. So, and this blockchain cannot solve this broadcast channel. So again, I'm not going through the technical detail, but you just can't achieve the termination property. So blockchains are not equal to broadcast channel. And we have to think about these when we are building this SMR channel from the first principle perspective. And this is just like a summary slide that I already mentioned. So broadcast channel assume that there is a known delta that every message is going to appear on chain. We can't guarantee that. And everybody sees them at the same time. We again can't guarantee that when we call blockchains in general. But the property that SMR achieves is still sufficient. We just have to make minor adjustment and solve the protocol. But why should we go that? Is that we are good at building. Now, what we have shown with starting with Bitcoin, Ethereum, and all new systems we build is that by now we are good at building blockchains. So once we build blockchain, now can we build privacy-preserving protocols based on them efficiently without reinventing the wheel is the attempt over here. So can I use blockchains or SMR and build privacy MPC protocol, multi-party computation protocol on top of that is a quest that we are looking into in this case. And while doing that, if we can do that more efficiently, even better. So the first thing, the core principle there to consider is secret sharing. I have a data and I want to post that on chain in a fashion so that nobody knows what that data is, and so that later it can be used. The prominent mechanism in that perspective is the secret sharing. It provides interesting properties over encryption in general. And if you're using broadcast channel, it required 51%. Again, required any honest majority, 51% honest party sufficient. If you can't assume synchronous or broadcast channel, you required much higher number of nodes. So the way to look at it this way is that when you say something as a problem I can solve for 15%, mean that I can tolerate many more bad parties in the system and my protocol will be still secure. But when you say 67%, that means even 33% of nodes go bad, things can go wrong. So whenever possible, I want to have a low number of honest party to make the system work. So what we observe is that if we assume this broad blockchain channel available magically, this whole problem becomes extremely easy. The only thing is what we have to know as non-interactive VSS, where non-interactive terms say you just create this VSS like an encryption and you just post that on blockchain. And everybody is going to see that in exact same order. We have to use some very simple zero-knowledge proof for that, but it can offer a very nice properties, and all our problem can be solved for honest majority. We do not require super majority for such thing to work. So, and in general, so here's the summary slide. So if you assume broadcast channel that it was assume more in academic literature, you can solve this problem 51%, but again, we can't assume that to be true. If you go to the pure asynchrony, you require many more parties and require more honest parties. But we assume that you have access to some blockchain, and that blockchain is fast enough, we can solve this problem much more efficiently, very easily, without requiring much programming on the developer end, using just 51% honest party. And that's a good way to start building such systems in such an environment. The next thing is now what is known as distributed key generation, or DKG. Some of you might have heard about the concept, where somehow you want to have somebody providing threshold signature on your environment, or basically maybe we can call it the more space efficient version of multi-signature, if you heard the multi-signature term. There also, this protocol can be built very efficiently on the SMR just by extending my verifiable secret sharing scheme. And where now what will happen is that we'll have some key which is secret shared on such an environment, so that nobody knows that key. But these parties, node 1, node 2, node 3, can themselves sign data for you, such that even when, as long as at least 2 of them in this example, or as long as 51% of them are honest, no incorrect signature can be generated, or only correct signature can be generated. So it's also highly relevant concept also from the account abstraction perspective as well, or building more complex escrow environment or any such privacy preserving solution. And again, this is the problem. If we don't build these solutions without SMR, just purely on the internet, we have to go for 2/3 honest majorities. But again, once we have access to blockchain, the problem becomes much more tangible and much easily solvable in such an environment. And again, programming becomes highly efficient. So my key theme, as you can see, is how to build these solutions assume that you have access to a blockchain, and how to make them efficiently and securely without having any issues or vulnerabilities present into such an environment. Right? So once we have such a thing available, it can be used to generate randomness services. So if you heard about VRF, like randomness services that required for gaming environment, or all others, even other DeFi environment, how to build that. Once you have such infrastructure I showed that's available, you can build these services very efficiently in a purely asynchronous manner, very simple programming. You don't need to, as long as you have SMR, your blockchain is working, everything will continue to function correctly. Okay, threshold ECDSA, EDDSA signature. That's like say you want to build signature for Taproot. This approach can be used in that perspective. Again, in a one more aspect is publicly verifiable manner. That means you can prove to the world that you are doing computation in a fashion so that anybody who comes and check that blockchain 10 years down the line can still know that you did that computation 10 years ago in a correct way. That's certainly something that's possible. And in general, multi-party computation or privacy-preserving computation that we want to perform, that can be built in what is known as threshold linear homomorphic encryption. And because many people, I assume, already heard about FHE, so this is the way to do it in technical level, but maybe I'll be happy to discuss, but I'm not going through the technical details over here. I make sure to add in case there's some technical audience who can catch a word, and then we can discuss later. But I want to even dedicate one slide to comparison between FHE and MPC, as I was trying to explain here. So I assume you heard about FHE. It's certainly something that's getting picked up quite a lot these days. And conceptually, FHE could be looked at as the one way to do multi-party computation in general. And there are multiple ways to do a multi-party computation. What I'm trying to show is what is known as secret sharing-based multi-party computation. And here is one slide where I'm trying to provide some comparison. And somehow, thankfully, with some graphical I got, so I want to show a bottleneck, right? So if you look at the fully homomorphic encryption, it's an expensive task. Okay, things happen you can continue to work on this environment. There is no communication that you have to perform per se that much, because everything can happen just on the blockchain. Okay, but it's an expensive task to add and subtract. On other hand, if you consider multi-party computation, as I was saying, it's network bound, where you have to do some interaction, you have to send some messages to the network to make it work. But in that respect, if my network is fast or network is good, but my computation available to the node is not so good, in that case, I should go for MPC, as I was mentioning. On the other hand, I have like extremely good machines, and my computation have lots of what we call as multiplication or processes which will require interaction. Then I should go for FHE. Is the approach. So they offer interesting trade-off that has to be considered when you're building solutions. But I can simply say anything that we can do with FHE or fully homomorphic encryption can be also done with this approach, and vice versa. But the idea is that there will be interesting trade-off present, which will just clearly demonstrate one thing or other as you required for your applications and your environment and use cases. So hopefully we'll see many interesting things happening in this space in this year as well as in the coming years. And we already have codes available for all these environments that people can play on and try to understand the things. And hopefully we'll see many interesting things getting built in production based on that. So in conclusion, I want to say that using SMR to build all these privacy-preserving solutions is a really good idea. It can allow us to have better resilience. We can tolerate more faults. But more importantly, it can make the development a very easy task, and that can play a significant role. In general, there are also interesting problems I keep putting there, like being in more academically oriented, how to prove these lower bounds and other things. But and there's a lot more to build here, but still things looks promising and very interesting to build upon. And thanks a lot for listening to this talk. I'll be around if you want to have some questions here, or if you want to reach me, you can reach me on Twitter, or you can just send me an email.
Great. Well, listen, thank you so much. Round of applause for Aniket, please. Thank you.